If you still believe that science has already deciphered the secrets of the cosmos, get ready for a turnaround that is leaving even the greatest experts open-mouthed. For decades, we thought that the universe obeyed well-established laws. But now, the James Webb Space Telescope, with its unprecedented precision, is dismantling much of what we thought we knew. Galaxies arising long before expected, gigantic structures organized as if they were planned, and anomalies that current physics does not fully explain. These are just the beginning. In the next few minutes, you will understand why we are living a true revolution in the way we see the universe and what these discoveries mean for the future of science. When the first data began to arrive from the James Webb Space Telescope, the team of astronomers simply could not believe what they were seeing. There, in the infancy of the universe, were images of already mature structured galaxies, bright and contrasting, that should have taken billions of years to develop. It was like observing a centenarian tree sprouting soon after the planting of the seed. The standard cosmological model predicted a much slower and more gradual growth, but James Webb exposed a reality in a hurry. What was most surprising was the complexity of these galaxies. Many already featured second and third generation stars, and more astonishingly, heavy elements such as oxygen and iron were present in significant quantities. This means these stars lived and died quickly to enrich the interstellar environment so soon. Even the boldest galactic formation models are challenged by this cosmic anticipation. As recent studies up to 2025 confirm that galaxies observed as early as 300 million years after the Big Bang are far more developed than expected. Scientists accustomed to working with extensive cosmic timelines now need to review their equations. The observations made with the James Webb Space Telescope indicate that the birth and growth of the first galaxies may have been much more efficient than any simulation suggested. Hypotheses propose extremely dense initial fluctuations as favorable conditions, but nothing conclusive has been established yet. This turnaround also sparks debates about the role of dark matter in this process. Could its initial distribution have helped shape these structures more quickly? Or perhaps there are still unknown physical phenomena interfering with the initial stages of cosmic expansion. Each new discovery defies prevailing logic, forcing science to seek answers in territories that once seemed too speculative, with ongoing research in 2025 exploring alternative models like modified gravity or early dark energy. As we try to decipher how these galaxies form so far, so soon, the James Webb Space Telescope begins to reveal something even more intriguing. Structures even bigger, almost as if the universe was organized in patterns that defy chance. This is where we enter the domain of the impressive organized cosmic filaments. Imagine the universe as a colossal web where galaxies are not randomly distributed, but connected by gigantic structures called cosmic filaments. In 2023, the James Webb Space Telescope revealed one of these structures composed of 10 galaxies aligned in a thread-like pattern dating back to only 830 million years after the Big Bang. This discovery offers an unprecedented view of the initial formation of the cosmic web. These filaments are not only vast in scale, but also exhibit surprising organization. Studies indicate they can extend for hundreds of millions of light years, with wave-like, regularly spaced patterns resembling a cosmic architecture. This symmetry challenges previous predictions based on simulations, suggesting forces or processes not yet understood are shaping these structures, with recent 2025 analyses refining our understanding of their formation. Beyond the James Webb Space Telescope, astronomers have identified about 978 galaxy groups, mapping the evolution of cosmic structures over 12 billion years. This sample, one of the largest ever observed, allows astronomers to study how galaxies form, grow, and interact over time, offering valuable insights into the large-scale evolution of the universe. The presence of these filaments and groups of interconnected galaxies suggests the universe has a complex underlying structure where matter is organized non-randomly. This organization influences cosmic processes from star formation to the dynamics of galaxy clusters. Understanding this cosmic web is essential to unraveling the mechanisms governing cosmic evolution. With ongoing surveys in 2025 providing richer datasets as we explore these vast structures, the James Webb Space Telescope continues to surprise by detecting gravitational anomalies in regions where there is no visible matter. These intriguing phenomena lead us to question what else might be hidden in the depths of the universe. In September 2023, the James Webb Space Telescope captured an impressive image of a distant galaxy identified as JWST ER1, surrounded by a near-perfect ring of light, known as an Einstein ring. This ring was caused by the distortion of light from a galaxy positioned even further away due to the immense gravitational force of the intermediate galaxy. What surprised scientists was the mass involved, approximately 650 billion times the mass of our Sun, far higher than expected. After subtracting the visible matter, researchers found that a significant amount of dark matter, about 5 to 6 times more than anticipated, was needed to explain the gravitational effect. This result, confirmed in 2024 studies, raises the possibility that dark matter has properties still unknown, perhaps interacting in ways our current models cannot describe accurately. This was not an isolated case. The James Webb Space Telescope also identified gravitational distortions in various other regions of space without corresponding visible matter to explain these deviations. These anomalous patterns challenged the traditional model of dark matter distribution, which had assumed a relatively homogeneous dispersion of this invisible substance throughout the cosmos. These findings, corroborated by 2025 observations, suggest we understand very little about the true constituents of the universe. The telescope's unprecedented deep infrared observation capabilities allow it to see these subtleties with a level of detail never achieved, forcing the scientific community to reevaluate the foundations of modern cosmology and seek new explanations for these mysterious forces. As we continue trying to understand these distortions of light and gravity, new observations reveal another intriguing phenomenon: rhythmic light pulses appearing in zones completely devoid of any visible source. A new enigma appears on the horizon. In early 2025, the James Webb Space Telescope captured an intriguing phenomenon: pulses of light perfectly rhythmic with intervals of approximately 29.437 seconds, emanating from regions of seemingly empty space. These signals persisted for 37 minutes before ceasing abruptly, defying conventional explanations. The absence of visible emission sources in these areas makes the phenomenon even more enigmatic. Astronomers have considered hypotheses such as neutron star pulsars emitting radiation at regular intervals. But the location in regions devoid of visible matter and the regularity of the pulses raise doubts about this explanation. Another theory suggests these could be manifestations of unknown physical processes, perhaps related to fluctuations in the fabric of space-time. As of 2025, no definitive explanation has emerged, and research continues. The precision of the intervals between pulses and their limited duration suggest a behavior that some consider intentional, though it is premature to assert any artificial origin. The regularity and abrupt cessation of the signals resemble communication patterns, a possibility that, while speculative, cannot be dismissed without further investigation. The James Webb Space Telescope, with its ability to observe the universe in infrared wavelengths, continues to reveal phenomena that challenge our current understanding. The detection of these light pulses in apparently empty regions highlights the importance of exploring the cosmos with new tools and perspectives. Each new observation may bring us closer to understanding the deepest mysteries of the universe. Spectral readings showed clouds composed of silicates, an abundance of oxygen, and a relative scarcity of carbon, contrasting significantly with gas giants in our solar system. The great enigma behind HIP 65426b is not only its composition, but also its formation. Conventional planetary formation models indicate that such massive planets should form closer to their star and then migrate. However, in this system, there is no clear evidence of a debris disk which would normally serve as a nursery for these planets. This suggests that something in the mechanisms of planetary formation still eludes us. Hypotheses under discussion in 2025 include gravitational interactions with other undetected bodies in the system that may have thrown HIPA 65426b into its wide orbit shortly after formation. Another more speculative possibility is rapid formation processes in outer regions of the protoplanetary disk, contradicting decades-old theories that place gas giant formation closer to the central star's heat and density. As we delve into these mysteries from distant worlds, a more audacious provocation arises. What if some of these planetary or cosmic structures are the result of interventions by advanced civilizations? This is precisely the territory where discussions on astroengineering and possible signs of cosmic intelligence emerge. The idea that advanced civilizations could modify cosmic structures on unimaginable scales has gained traction in scientific discussions. Astrophysicist Abraham Lowe, a professor at Harvard University, proposes that such civilizations could undertake astroengineering projects, rearranging matter on a galactic scale. A theoretical example is the construction of Dyson spheres, megastructures that surround a star to capture its energy, a concept originally proposed by Freeman Dyson in 1960. In 2024, researchers identified several stars with unusual infrared signatures that could be candidates for Dyson spheres, though no confirmation has been established as of 2025. If confirmed, these structures would indicate civilizations capable of manipulating stellar energy on a vast scale. Furthermore, Lowe suggested that the interstellar object Oumuamua detected in 2017 could be an artificial probe sent by an extraterrestrial civilization. This hypothesis, though controversial, highlights the importance of considering non-conventional possibilities in the search for extraterrestrial intelligence. The construction of megastructures like Dyson spheres would require extremely advanced technologies, including the ability to dismantle planets for materials. Stuart Armstrong, a mathematician and philosopher, has discussed how humanity could become a Type II civilization on the Kardashev scale by constructing a Dyson sphere around the Sun using materials from planets like Mercury. As we explore these possibilities of astroengineering, studies indicate similar patterns across the cosmic web and the neural networks of the human brain, suggesting that the universe and the mind may share a common informational structure. In 2020, a study led by astrophysicist Franco Vazza at the University of Bologna and neurosurgeon Alberto Fletti at the University of Verona revealed an intriguing parallel between the architecture of the universe and the human brain. The team compared simulated galactic networks with microscopic brain tissue slices, analyzing mathematically how matter is distributed in both systems. Despite the colossal difference in scale, the universe spanning about 93 billion light-years and the human brain a few centimeters, the structural similarities were striking. Both the brain and the cosmic web exhibit networks formed by nodes and connections. In neurons, axons interconnect cells. In the universe, filaments of dark matter connect galaxy clusters. In both cases, about 30% of the total mass is in the nodes, while 7% is in dispersed connections. According to the researchers' volume density analysis, these patterns reaffirmed in 2025 studies suggest certain principles of self-organization may be universal in nature. Another curious fact raised by the study is the complexity of the two systems. The human brain contains approximately 86 billion neurons, while the observable universe contains around 100 billion galaxies. Though a numerical coincidence, This similarity reinforces interest in exploring these parallels from computational and formational perspectives. The authors highlight no direct causal relationship between the systems, but a mathematical convergence pointing to universal rules of network optimization across vastly different scales. Nature seems to favor structures that maximize communication and energy efficiency, while maintaining organized densities across vast physical spaces. This intrigues researchers in statistical physics, cosmology, and neuroscience who are seeking common explanations based on complex network theory, with 2025 research deepening these investigations. As scientists unravel these fascinating intersections between the cosmos and biological systems, new discoveries point to limits in the current scientific model itself. Recent observations suggest that our laws may be superficial approximations in the face of the universe's true complexity. The recent discoveries of the James Webb Space Telescope have challenged established cosmological models, suggesting that our current laws may be superficial approximations of a more complex reality. Observations of mature galaxies formed only 300 million years after the Big Bang. Cosmic structures with unexpected symmetry and gravitational anomalies without evident explanations indicate the universe may operate on principles not yet understood. Modern physics, based on the Standard Model and general relativity, faces difficulties explaining phenomena like dark matter, dark energy, and cosmic inflation. These gaps, highlighted by 25 findings, have led scientists to consider the need for a new paradigm incorporating concepts of information, memory, and self-referential complexity. For example, loop quantum gravity and Roger Penrose's conformal cyclic cosmology propose alternative models for the universe's structure and evolution. The integration of disciplines like information theory, neuroscience, and complexity science has revealed similar patterns between apparently different systems. Studies comparing the cosmic web with human brain neural networks suggest universal principles may govern the organization of complex systems across scales. This interdisciplinary approach, gaining momentum in 2025, may be fundamental to developing a more comprehensive scientific model. Adopting a new scientific paradigm will require reassessing the foundations of physics and cosmology, as well as incorporating new mathematical and computational tools. Artificial intelligence and big data analytics are already playing a crucial role in identifying patterns and formulating hypotheses in large astronomical datasets, accelerating the transition to a more robust and comprehensive model of the universe. As we explore these possibilities, it is essential to maintain a critical and evidence-based approach. Science progresses through constant review and improvement of its models, and the observations of the James Webb Space Telescope offer a unique opportunity to expand our understanding of the cosmos and develop theories that more faithfully reflect its complexity. Now that you have encountered these impressive discoveries, tell me, are we really close to understanding the universe? Or is everything we know so far just the tip of a cosmic iceberg? How many other hidden laws of nature are still waiting to be revealed? And if the rules that govern everything around us are actually far different from what we learned, the great truth is that we have never been so close to redefining science as now. Whoever follows these discoveries from the beginning has a unique chance to see history being rewritten. So take advantage and subscribe now to the channel. Activate notifications and come with me to see what the James Webb Space Telescope and science will reveal next. Honestly, what is to come may be even more surprising.